Loop quantum gravity's dream is to directly quantize general relativity itself, without extra dimensions, without supersymmetry. In 1986, Ashtekar proposed new variables, replacing the metric with an SU-2 connection, making GR quantizable like Yang-Mills theory. This is the starting point of LQG. The core idea is quantum geometry. Spacetime is discrete at the Planck scale, built from spin networks and spin foams. Today we discuss, after 40 years, how far has LQG come toward the ultimate goal of a theory of everything. To understand loop quantum gravity, we must first understand the problem. Einstein's general relativity tells us gravity is the curvature of spacetime, described by the Einstein field equation g mu nu equals 8 pi gt mu nu. Planck's quantum mechanics tells us that the Planck length p equals square root g/c superscript 3 is almost equal to 1.6 times 10 superscript 3 meters. Spacetime itself must be quantized. In 1986, Indian physicist Ashtekar achieved a key breakthrough, replacing the metric field G with an SU-2 connection A, making GR quantizable like Yang-Mills theory. This is the starting point of loop quantum gravity. The core of LQG is quantum geometry. Classical geometry is continuous and smooth, but quantum geometry is discrete at the Planck scale, built from spin networks. The spin network concept was proposed by Roger Penrose in 1971, edges labeled by spin quantum numbers J equals 0 1/2 1 3/2 2, nodes labeled by quantum states. The area quantization formula is A equals 8 pi gamma p superscript 2 sigma square root, J plus 1, where gamma is almost equal to 0.2375 is the Barbero-Emerzi parameter, determined by black hole entropy. The volume quantization formula is V equals sigma q, each node corresponds to a volume quantum. This means that the Planck scale, area, and volume cannot vary continuously but take discrete eigenvalues. Key techniques include Ashtekar variables and spin foams. Ashtekar proposed in 1986 replacing the metric field gauge with SU-2 connection AIA, making GR writable in Hamiltonian form similar to Yang-Mills theory. The canonical quantization commutation relation is A, x, E, y equals I kappa delta, xy, requiring Gauss, diffeomorphism, and Hamiltonian constraints. Spin foams were proposed by Lee Smolin and Carlo Rovelli in 1993. Time evolution of spin networks forms two complexes called spin foams. The 2008 EPRL model gives 4D Lorentz invariant transition amplitudes Z equals sigma pi A, V, pi B, E. LQG has achieved several major successes. Thomas Thiemann proved in 1998 that the Big Bang singularity can be resolved by quantum geometry effects. Ashtekar, Pawlowski, and Singh established loop quantum cosmology in 2006. Discovering the Big Bang is actually a big bounce. Carlo Rovelli calculated black hole entropy using LQG microstates in 1996, with area eigenvalues naturally giving the correct Beaconstein-Hawking entropy S equals S/4p superscript 2. Spin foam models are naturally UV finite, requiring no renormalization, contrasting sharply with string theory's infinities. Most importantly, LQG satisfies background independence from the start, with spacetime emerging from quantum states. LQG's biggest challenge is unresolved dynamics. The Hamiltonian constraint H psi equals 0, Wheeler-DeWitt equation, has no agreed-upon correct definition in LQG. Thomas Thiemann attempted in 1998 using the Holst action and Thiemann trick, but results depend on specific gauge choices. The core controversy involves different researchers, Carlo Rovelli, Thomas Thiemann, Jorge Pullen, and Rodolfo Gambini, proposing different quantization schemes yielding different results. Currently, loop quantum cosmology is a successful simplified version, but full 3+1 dimensional LQG dynamics remains unestablished. LQG's second challenge is the difficulty of the semiclassical limit. The core question: how to recover classical spacetime from quantum geometry? This requires collective behavior of many spin foams producing smooth spacetime, WKB approximations satisfied, and classical Einstein equations emerging from quantum constraints. But the EPRL model's behavior at large spin limit is not fully understood, and semiclassical limit construction is much harder than in string theory. String theory has fixed backgrounds with easy semiclassical limits. LQG has background independence, making semiclassical limits the core difficulty. Numerical simulations of spin foams haven't fully matched classical gravity. LQG's third challenge is including standard model particles. String theory naturally contains standard model particles as different vibration modes of strings, but LQG quantizes gravity directly without involving matter fields, requiring external introduction. No principal guides which matter fields should be included. A possible is that excited states of spin networks might correspond to matter particles, similar to emergence phenomena in condensed matter physics. Lee Smolin suggests matter may emerge from microscopic degrees of freedom of quantum gravity, but no concrete model exists. Research in this direction is very preliminary. LQG's fourth challenge is experimental tests. LQG predictions include area and volume are discrete, minimum area p superscript 2, big bounce, speed of light may depend on energy, Lorentz symmetry violation, characteristic signals in primordial gravitational waves. Test pathways include CMB primordial gravitational wave signals, gamma-ray burst photon time delays, neutron interferometry tabletop experiments, and gravitational wave observations of Planck scale effects. Currently, no LQG prediction has been experimentally verified, but LQG predictions may be tested earlier than string theory through cosmological observations. Loop quantum gravity and string theory are two different approaches to quantum gravity, each with strengths and weaknesses. LQG's basic objects are spin networks and spin foams, string theories are strings. LQG is four-dimensional. String theory needs 10 or 11 dimensions. LQG satisfies background independence, string theory doesn't. LQG doesn't need supersymmetry, string theory does. Both calculate black hole entropy, but LQG resolves singularities while string theory doesn't. Smolin argues LQG is more fundamental, Witten argues string theory is the unified theory. No conclusion yet. Loop quantum gravity may be correct, but there's a long road to a theory of everything. Reasons for optimism: singularity resolution successful, big bounce is an important prediction, black hole entropy consistent with string theory, background independence is a fundamental advantage, may combine with condensed matter physics methods. Reasons for pessimism: dynamics not fully resolved, semiclassical limit construction difficult, matter content unclear, experimental tests far away. My judgment: LQG may be correct, but becoming a TOE still requires 30 to 50 years of key progress. Greatest hope comes from cosmological observations. Primordial gravitational waves and CMB may provide decisive evidence in the future. Loop quantum gravity has profoundly changed our understanding of quantum spacetime. Whether or not it becomes a theory of everything, the exploration itself is already written into the history of science. Thank you all.